All right. Hello, everyone. Thank you for coming. It's a pleasure to have here today with us Dr. Antonio Ortega from University of Southern California. Professor Ortega received his telecommunication engineering degree from the Politécnica de Madrid in 1989, and he got his PhD as a Fulbright Fellow from Columbia University in 1994 when he joined USC as a professor or assistant professor, where he is currently a full professor and associate chair of EE systems. He's very well known in the area of multimedia compression, communication, and signal analysis. He's also the founding editor-in-chief of the SPIPA Transactional Signals and Information Systems, and he received several awards, particularly the NSF Career Award and the IEEE Communication Society Leonard Abraham Prize Paper Award. And it's a pleasure to have him here. He'll talk to us about some of his recent work on wavelets, on graphs. It's a pleasure to have you. Thank you.
Thanks a lot, Hamid.
The floor is yours.
All right, and this is by far the longest anybody has had to wait to hear me talk. So I hope it's worth your time.
My apologies.
Not a problem. And one option would be to do my slides in 30 minutes. Maybe skip every other slide.
No.
No? Okay. Then
Just go ahead.
Okay, I guess I'll go then for the full talk. So this is work that I've been doing the last several years. I'm sure it's a feature. All right, so let me start it. So I first acknowledge a lot of people that have collaborated on this work, and primarily Sunil Narang and Godwin Shen, who are the two PhD students whose work I'm describing here. Mostly Sunil's work, but a number of collaborators in various places as well. And most recently, this is work that is funded by NSF. All right, so this is the plan. I'm going to keep the introduction at a very high level. And I think if you've done a signal processing class at some point in your dark past, you'll be able to follow most of it, I hope, and before we go into the details of what we're doing with the graphs. And then I'll spend maybe half the talk talking about a few applications, and those I won't describe in a lot of depth. I just want to give you a flavor of things that we can do. Okay, so as motivation, we're interested in graphs, and graphs can represent many different things, and this is motivation to work on generally tools that allow us to represent graphs. And this goes from graphs that we might use in computer graphics to a graph that you may encounter in a sensor network application to, for example, looking at images as graphs, where every pixel in the image represents a node, and the level of connectivity is captured by the graph. Okay, but also beyond this, we may have social networks as an example of graph data sets, and we also may have things like finite state machines, graphical models that are also captured by a graph. Okay, so that you encounter graphs in many places, and when you think about graphs, you don't necessarily think about signals. Okay, part of the goal here is to start thinking about graphs in terms of signals that live on those graphs, and then see what we can do with those. Okay, so for the purpose of this talk, we're going to consider these very abstract graphs. We don't expect a particular form of connectivity. We're going to have vertices and links. We will have weights, and we will consider graph signals. Okay, so this is a key point. We assume that the topology of the graph is given, so the nodes and the vertices are there and they're connected in a certain way, and that doesn't change. But then at each of the nodes, there's a scalar or vector value, and that vector of scalar values is the graph signal. Okay, so the graph signal is whatever data is available in the vertices of the graph. Okay, so we would like to develop techniques to analyze, compress, store data in the graph signals. And I think an important point to make is that we want to develop tools that make use of the connectivity into the locality in the graph. If you think about a graph signal, if you have an n node graph, this is a vector of dimension n. What we would like to do is process it in such a way that we take into account the fact that these two nodes are connected, but this node is not directly connected to this one. Okay? So we cannot just treat this n-dimensional vector as a vector and treat it with standard tools. We want to take into consideration the topology of the graph. Okay? So point to remember, we're dealing with graph signals, and we want the analysis of the graph signals to take into consideration the topology of the graph. And for that, we will introduce wavelets. Okay, so we'll get there. Why wavelets? Well, we're interested in situations where the data sets are very large, and so manipulating these data sets in a global manner may be too complex. There will be situations where some notion of frequency will be useful in analyzing the data, and so we will also want to take these massive data sets, simplify them, go to coarser graphs, then do the processing there, and then estimate from the result in the coarse graph a solution to the full graph. Okay, so we're interested in localized processing. We're interested in the notion of frequency, and we're interested in being able to simplify the graphs to smaller size graphs that we can analyze. Okay, let me spend 2 slides on wavelets. For the purpose of this talk, I'm only interested in the analogy with discrete time wavelets, and for our purposes, you can think of the discrete wavelet transform as consisting of filter banks, okay, where you have a low-pass filter, high-pass filter, followed by downsampling. You need downsampling so that you can have a critically sampled representation, so that you have as many samples here as you had at the input. And these are invertible transforms, potentially orthogonal, so you can basically synthesize back by upsampling and then reconstructing. And with this simple 2-channel filter bank, which has been widely studied in signal processing, you can construct transforms that are much richer, for example, by doing what are called dyadic decompositions, where you take the low pass and decompose it successively. Okay? And I put this here because basically we're going to design 2-channel filter banks for graphs. Okay? So that's going to be our basic building block. Okay? And in regular signals, even a 2-channel filter bank has been shown to be very useful. In dealing with 2-dimensional images, this will also come in handy a bit later on. The typical approach to deal with 2-dimensional images in practical cases, for example, things like JPEG 2000, is to basically perform 1D filtering horizontally and then perform 1D filtering vertically. Okay? Which means that, again, with a 1D filtering operator like this 2-channel filter bank, you're in good shape. And of course, there are other methods that do non-separable filtering, non-separable downsampling, but by and large, for many applications, the separable 2-channel filter bank is a very good option. Okay, so keep this in mind as well. All right, so as far as the talk is concerned, I'll talk a little bit about introducing concepts and what you could say is graph signal processing. I'll introduce some lifting-based filter bank designs, and then some spectral-based filter bank designs. And then I'll cover a bunch of applications, each of them probably spending 2-3 slides on them. Okay, so about half the talk will be tools, and half the talk will be examples of what we can do with these tools. Okay, so graphs 101. Again, we have vertices connected by some edges. Given the topology, in all of this work, we assume the topology is fixed. Okay, so it's given to us. We define an adjacency matrix that just tells us, in this case, we're considering undirected graphs, potentially weighted. So we have an adjacency matrix that captures that node 13 connects to node 18, right? So this is typically a fairly sparse matrix that captures the connectivity in between nodes. Then we have a degree matrix that is diagonal and has the degree of every one of the nodes in the graph. We define the Laplacian matrix. There's various flavors of the graph Laplacian, degree minus adjacency or normalized version. And this will be used, I'll describe how. And we define a graph signal. And again, the graph signal for our purposes here, a scalar, and it's basically one scalar associated to each point in the graph. Okay? All right. So frequency analysis of signals in a graph has been done to a large extent, and it's typically based on the eigenvectors of a graph Laplacian. Okay, and so you can think of the eigenvectors of this graph Laplacian as a full set of orthogonal vectors with eigenvalues corresponding to them, and this eigenpair provides a Fourier-like interpretation for graph signals. In other words, if you take a graph signal with n values, because this is an orthogonal basis for Rn, you can represent the graph signal as a projection onto each of these vectors. Okay, so this is well known. I think what's interesting to see is that these can really be interpreted as frequencies, and this is best seen with an example. Okay, so here what we have is basis of the DCT. Okay, so low pass to higher and higher frequencies, and to first order, it's nice to you can see that each of these basis functions has an increasing number of zero crossings. Okay, so this is all positive. This goes from positive to negative, positive, negative, positive, etc. So the more zero crossings you have, the higher the frequency. Okay. Now look at the eigenvectors of a graph Laplacian for a very simple graph, and the lowest the eigenvector corresponding to the lowest eigenvalue is constant. Okay, so DC, and as you go to higher and higher eigenvalues, you have more and more sign changes in the graph. Okay, so a key point is that the sign changes are in the graph. So for example, we don't care that this node and this node have a different sign because they're not connected, but it matters that this node and this node have different sign because they're connected. Okay, so you can interpret the zero crossings in the graph as a notion of frequency, and even if you go to more complex graphs like this one, you see the same thing. Okay, so this is a more complex graph. Lowest eigenvector, basically constant signal in the graph. If you go to the highest eigenvectors, you have lots of sign changes. And you can see here, from lowest to the next lowest, there's only one place where there's a sign change. Here there's several places, and so forth. Okay, so they have a nice frequency interpretation, and so there's a lot of intuition you can derive from this. So eigenvectors of graph Laplacian to us are the same thing as the discrete Fourier transform. If you were dealing with standard finite length signals. Okay, so when we talk about these graph transforms, of which the graph Fourier transform is an example, we're looking to transform an input signal. The signal is the graph signal. Okay, so that's what we're doing, and then we would like to transform and then do some processing or analysis. We would like to be able to do this with arbitrary graphs, and we would like all these properties to be there. We want this to be invertible and critically sample, orthogonal, etc. Okay. One important point is that once you think about the graph spectrum, you can also think about localization. So if you've done a course on wavelets, the first thing you hear about wavelets is, well, they provide a trade-off between time and frequency localization, right? Well, in the context of a graph, the frequency localization is in terms of the graph spectrum, right, which is derived from the graph Fourier transform. And the spatial localization is how localized things are in the vertex domain. Okay, so that, for example, a basis might be very localized if it's non-zero only within k hops of one particular node. Okay, so in graphs, you can also think in terms of localization in space, in the vertex domain, and in frequency. Okay. All right, so a bit of related work, and then we'll go into contributions. There's basically been not a lot of work in developing wavelets for graph signals, and I think the earliest that I'm aware of is Krovera and Korasic in 2003. So you have designs that are based on the the vertex domain, and you have spectral designs. These spatial domain designs, some of them at least, are critically sample. Okay, so if you have n nodes, you have n wavelet coefficients, but they don't have a very easy frequency interpretation. And these frequency domain designs, they're not critically sample. Okay, and so we're sort of bridging the gap by having designs that are frequency based and critically sample. Okay, that's I would say our main contribution. Okay, so I'm going to talk about two methods. One that is lifting based and helps us get some intuition, and that's a spatial design. And then I'll talk about the the spectral design for these transforms. By the way, feel free to interrupt at any point if you have any question, anything that is not clear. Okay, so the lifting approach, for those of you who've done, studied again wavelets in image domain, the basic idea is to take the signal and to select, in this case, the graph, and divide the nodes in the graph into even nodes and odd nodes, two sets of nodes. And it's basically a transform that uses, let's say, even nodes to process odd nodes and vice versa. And by virtue of being this ladder structure, it's invertible. Okay? So essentially, in the case of a lifting transform, all you need to do is select even and odd nodes, and you have an invertible transform. There's a little bit of a catch that will come in a minute. Okay, this is most easily shown with an example. This is our initial graph. Can be completely arbitrary, doesn't need to be mapped to Euclidean space or anything. In this arbitrary graph, we simply decide that some nodes are even, some nodes are odd. Okay? And how to do that we'll discuss in a minute. And then what we do is we first, for every odd node, we use information from their even neighbors. So, and what we do is a prediction. So we predict from the even neighbors a value for the odd node. If the signal in the graph is very constant, this prediction will be very accurate. This value will be small. So this is sort of like a high-pass filter, right? So this will be large. This difference will be large only if the signal is not smooth in the graph. Okay? So this is the prediction part. And then the update part performs a sort of low-pass filter by feeding back to the nodes that have not been processed an average of the differences that were computed in their neighbors. Okay? So think of it as a low-pass, high-pass. But because half the nodes are used at each time, it's actually invertible. Now, the catch is that, in fact, if you have an initial graph that is arbitrarily connected, once you decide on even and odd nodes, you're essentially removing some edges from the graph because there cannot be processing that involves an even node and an even neighbor. So any link between nodes of the same parity is not used. Okay? So essentially what we're doing here is we're going from an initial graph to a bipartite graph where every node is connected only to nodes of a different parity, and then we do the processing in this bipartite graph. And I'm not going to talk a lot more about this, but just make the point that these are two examples of a bipartition for the same initial graph. And you can see that this bipartition, whereas you can do a very good transform on it, you're actually eliminating lots of nodes. There are lots of connections that are missing. So in this problem, as in others that I will describe a bit later, you have a solution after you choose a bipartite decomposition, but choosing the right bipartite decomposition is non-trivial. Okay? So you could do a transform, but this might be a bad even-odd assignment. This would be a good even-odd assignment. Okay? So this is the lifting approach. Now let me talk about the spectral approach. Okay? So remember that I mentioned that there are some spectral-based transforms, but they just are not critically sampled. Okay? So our key contribution here is to figure out how to deal with downsampling. Okay? All right. So what we're going to do is design critically sample two-channel filter banks. We're going to take the whole graph, and then we're going to choose two subsets of nodes. So it's similar to the even-odd assignment that I just described. And then we will filter but sample the low-pass output only in some nodes and the high-pass output in the other nodes. Okay, that's what we're going to do. And we have several solutions. I'll focus mostly on the orthogonal case, which was published last June. And there's a further solution that we've developed. Okay, our starting point is one of the two papers that I mentioned. There was one diffusion wavelets, the other one is spectral graph wavelets. This is a group at EBFL did this work. And what they have is a design of wavelets that are not critically sampled, and they can be defined in the spectral domain. Okay, so let me explain that. This is the range of the eigenvalues of the graph Laplacian. This implementation essentially projects a signal onto the eigenvectors of a graph Laplacian and then multiplies this by a diagonal matrix and then inverts. So what is this doing? This is essentially exactly the same as computing a filtering operation in the DFT domain. Okay, so you first go to the DFT domain, then you have a filter characteristic that is different weights to different frequencies, then you do the inversion. It's exactly the same thing. Okay, so think of this as going to the frequency domain, then multiplying by one different weight for each frequency, and then doing the inversion. So a profile like this would describe one of these filtering operations. Okay, there's one more step, which is that actually if you take a profile and you make it a polynomial, so if this h of lambda is a polynomial of degree k, that operation is actually Khop localized in the graph. Okay? Okay, so this is work that they proposed, and what I would like you to remember is this, that you can implement any filtering operation h of lambda in the Fourier transform domain, okay, or in the graph Fourier transform domain. That's the first thing. And second, if that operation, if this kernel is polynomial in lambda, then that operation is Khop localized. Okay, so those are the two key ideas. Okay, now let's talk about downsampling, and we'll come back to the filtering operation. Okay, so we're going to focus on downsampling and upsampling operation. So if you've looked at your signal processing course, you have that downsampling followed by upsampling is essentially you take a regular signal and then every other sample is replaced by 0, right? And what you're doing in the graph case is exactly the same thing. So we have a graph with a signal, and then every other, some of the samples are set to 0, the others are the same. Okay, so this would be the downsampling upsampling operation. In the frequency domain for regular signals, we know that this operation means that the spectrum of the new signal, this one that has the that has been upsampled back, contains the spectrum of the original signal plus a version shifted to pi of the original signal. Okay, and so the question, well, if we do this in a graph, what happens? Okay, so that was what we set out to find out. Okay, so to do that, we define a function beta, which for any vertex in the graph takes values either plus minus 1. So if we're in a node that we want to preserve, the value of beta is 1. If not, minus 1. Okay, and then trivially, you can see that the graph signal after downsampling and upsampling will be the original signal plus beta times the original signal, right? So if this is 1, then you have 2 times the original signal. If this is minus 1, you get 0, right? So that's straightforward, same thing as you would do for regular signals. Okay, so you can represent this in diagonal form by saying, in vector form, this is the vector of the graph signal. J beta is a diagonal matrix that has plus minus 1 in the right places, multiplied by f. So you have a signal that is f plus f tilde. Okay, so you have something similar to what we saw before, the spectrum plus the spectrum shifted to pi potentially. But do we have the same property that it's really a shift in the spectrum? Well, it turns out that that property exists if the graph is bipartite. Okay, so that's a key result for our design. So if we have a bipartite graph, okay, so that is a graph where we have 2 colors and there are no links between nodes of the same color. In this case, it turns out that if you take the spectrum of the original graph signal, and the graph signal can be anything, okay, and then you look at the spectrum of the graph signal plus this error term, it's actually just as in the regular domain, we have that it's a mirror spectra. So if this was primarily a low-pass signal, this is primarily a high-pass signal. Okay. So in the case of a bipartite graph, if you keep these nodes and set to 0 these nodes, you have exactly this property. And basically what it means is that J beta operation maps one eigenvector into another eigenvector. That's essentially what it does. Okay. So for example, it will map the lowest frequency eigenvector into the highest frequency eigenvector. Okay? And that's only for bipartite graphs when we have downsampling involving just keeping one color and setting to 0 the other one. Okay, so this is for the bipartite case. All right, so now we're ready to look at the design of a 2-channel graph filter bank. And the graph filter bank looks like this. We have filtering operations You know, this is the same structure as in the regular domain. We have low pass, high pass. The downsampling, there's a little twist where we preserve the low pass in some nodes, and then we preserve the high pass in the other nodes. Okay, and then the reconstruction would be we would upsample back, right? So this operation is what we just described, the downsampling, and then we would do low pass filtering, high pass filtering, and then we add this back. And of course, what we would like is f had to be equal to f, right? Now, in this scenario, we will be using the spectral filtering approach that I described before. Okay, so remember, Fourier transform, diagonal matrix Fourier transform. That's equivalent to just implementing the filter in the Fourier domain. Okay, and that means that for every one of these filters, all we care about is h of lambda. H of lambda or g of lambda. This is basically what describes. It's a function of lambda that describes how the filter operates in the frequency domain. Okay. All right. So now we can take into account these two downsampling operations, and we can construct the response of this system, right, with two-channel filter banks. You can see low pass analysis. This 1 plus j beta there, 1 minus j beta here. Basically, this captures the downsampling, upsampling in each branch, right? Remember, it was f plus j beta f, right? So that's what happens here. And then this is reconstruction filters. Okay, so this is just taking these blocks, whatever they are, and writing them. And as you would do in a two-channel filter bank design for regular signals, you can group this into two terms, one where the frequencies have been scrambled by this j beta operation, and one where they have not. And for perfect reconstruction, to recover f, what you would want to do is for this term to be 0, and you would want this term to be identity. Okay, and so we're going to see how we can do that. Okay, so basically the solution we have is a solution for the bipartite graph case, and then I'll describe how we extend this to general graphs. Okay, so for the bipartite graph case, we select these filters. So let me do this for. There's a downsampling function. Here's the key point. Remember that in the downsampling case, we have this frequency flipping, right? Well, that translates into filtering with a filter that has been frequency flipped as well. Okay, so if we original filter was h0 of lambda, h0 2 minus lambda is basically the reverse. Okay, so I should say that in the case of bipartite graphs, lambda is always between 0 and 2. Okay, 0 is an eigenvalue, 2 is an eigenvalue. Okay, so essentially you can see this as the equivalent of h of a to the minus j omega, right? It's basically shifting the filter to pi. Here it's converting a low pass into a high pass. Okay, so that's the key observation for bipartite case. And then you can write all these equations in the lambda domain, and this is equivalent to saying that the second term has to be 0, and this second term, for it to be identity, has to be a constant. And for the orthogonal case, you would get the solution. So let me talk about what the solution would be. So we call this graph QMF in analogy to the quadrature mirror filter approach for standard filter banks. And the ideas would be to select the low pass synthesis as the same as the low pass analysis, high pass synthesis same as the high pass analysis. And then basically the high pass analysis is just a frequency shifted version of the low pass. Okay, so if you've done a wavelets class, at some point you'll see this is exactly the same as the graph QMF, except that we're talking about the graph frequency domain instead of the standard frequency domain. Okay, and then what we do is, given all of these conditions, we're left with designing one filter that has to have this property, and basically the way you read this is that it has to have a flat frequency response. And we have a couple of designs for that, one of which is to design H0 to be an ideal filter, and the other is sort of a Mayer-like filter which is ideal but then has a smooth decay. Okay, and both of these things work. As I mentioned earlier, if we want these filters to be exactly localized, then you just need to make them polynomial. So for cases where we want exact localization, these designs are orthogonal. We can make them exactly localized, but we lose orthogonality. Okay, and so by using a polynomial approximation. And so this is an example. Again, this is 0 to 2. This is the frequency domain for any bipartite graph. This is the low pass, high pass, right? So you can see that, the decay. And this is the approximation of the graph QMF solution with a Mayer kernel for m equals 2, which means 2 Khop localized. So, I don't think you need a lot of signal processing to tell you that these are not very good filters, right? They're not very selective in frequency. If you increase m, that means that you allow higher polynomial degree, less localization in the graph. These filtering operators become better. You can see that you get a fairly nice response for, this is a 14 Khop approximation. Okay. We just made available on archive a biorthogonal solution, which is not orthogonal, but is exactly localized and perfect reconstruction. And that's we were going to submit it soon to also transactions and signal processing. But there's a catch, of course, that not all the graphs are bipartite. And remember that the solution for the lifting case was also requiring us to operate on a bipartite graph. Okay, so not all the graphs are bipartite. So I'll describe how we deal with that. And I think there's plenty of open questions there. And this is just one method that we've done so far. But there's probably other solutions. And the solution is really inspired by the approach that is used for images that I described in the beginning. Right? Images are not 1D, but one treats them as if they were 1D by doing row-wise filtering and then column-wise filtering. So we're following a similar philosophy here, except that things are more complicated because the graphs are arbitrary. So the idea is to iteratively decompose a non-bipartite graph into k bipartite subgraphs. Okay? And then each of them is filtered. And I think this is easiest to explain with an example. So let's say this is our graph, and it's not bipartite, right? But we can approximate it by a bipartite subgraph. And so what that means is that in this approximation, this is one color, this is the other. We only consider links across colors, but not links within colors. Okay? So we know how to design a transformation that uses only these links. And so what we do is essentially we ignore the other links first and then do a transformation only with these edges. That would be equivalent to doing row-wise filtering. Okay? And then once we're done with that, we're left with low-pass and high-pass information at each of the nodes. Then we put back the links that we ignored in the first iteration. Okay? We put them back, and now we do a second pass of filtering, which again gives us low pass and high pass. Okay, so this would be a direct analogy with the way we treat images. Okay, so we first filter only across these links. Okay, let's say row-wise in the image example. Then we're left with low pass, high pass values. We put back the other links, and then we have all 4 combinations: low pass across the first set of edges and the second set of edges, all the way to high pass across both sets of edges. Okay, so that's how we do the approximation. I think there's still research to be done on other approaches. So you would have, in analogy with the 2-channel, with the image case that I showed in the beginning, first subgraph, second subgraph, right? And before it was rows, columns, right? So that's sort of the analogy. Okay, let me show you an example to illustrate how this would work, and then I'll go on to applications and just give a flavor of different things that we're looking at. So this is the Minnesota traffic graph, and we arbitrarily created a signal on that graph, which has a constant value, and then has another constant value here around the Twin Cities. Okay, so just an arbitrary example. So we have this very complex graph, right? Even though it's a planar graph, but there are lots of connections. So to apply the transform that we're proposing, we start by dividing it into 2 bipartite subgraphs. Okay, so each of them has 2 colors, and there's only links between nodes of different colors. Okay, and then we would apply a transform that has low pass and high pass channels across the different subgraphs. And you can see that when you look at low pass in both subgraphs, you have something that looks very much like the original signal. It's just that it's being downsampled. And when you look at the high frequencies, you can see that there's actually high energy around the boundary area. And if you reconstruct from that information, the reconstruction from only the low frequency gives you a pretty good approximation to the original signal. And the reconstruction from only the high frequencies captures high energy only in the boundaries between the two regions. Okay, so it does something reasonable that we, that we can interpret. Okay, so I'm going to move on to applications. But are there any questions on what I described so far?
So, how complex is it to actually for an arbitrary graph and get all the possible bipartite? Is that is that an easy?
It's not an easy problem. One of the solutions we have is to actually start by coloring the graph, and then once you have the coloring, there's a structured way to do the bipartition. And like I said, we're also exploring other approaches that are not exactly like this. Any other questions? All right. So for the applications, I guess what we use, all they have in common is that there's always going to be a graph. Okay, that was no surprise. So I'll try to make clear what the graph is and how we find it or decide what it should be, and then I'll give you a flavor of the processing and results. Okay, but I'm mostly interested out of the second part to convince you that there's lots of things that you could look at as graphs, and then there's emerging tools that one can use to process them. Okay, so the first example, going back to my distant past on video encoding, this is some work with some colleagues in Madrid, where we were looking at the video encoding that allows some kind of directional transformation, and typically there have been lifting-based filtering operations, but they tend to apply the filtering independently in space and time. And so we wanted to see what could be done if one would want to deal with space and time at the same time. Okay, and so, as I said, start by defining the graph. And here the graph we're defining involves the pixels in consecutive frames. Okay, so this is one frame, the next frame. What we do is first we will determine temporal relationships between the pixels. That means that if a block in this frame can be predicted by a block in that frame, then their corresponding pixels are linked. And we also have one twist on this, which is that we identify edges in the image. And what we do is we consider that pixels that are on opposite sides of an edge are not really connected. They're not strongly connected. Okay? So what we do here is both motion estimation and edge detection. And so once you have this, you can link the pixels. As I said, there's a temporal link based on motion. And then there's a spatial link where we avoid connecting across edges. Okay? And so that gives us a graph that is arbitrary. It doesn't mean, pixels don't necessarily have full set of neighbors either temporally or spatially.
So how do you define, do you assume that the edges are have been identified already?
Right. So we take that into account, and we in our implementation, what we do is we do edge detection for the first frame, and then we carry that with the motion estimation. So essentially, we would transmit edges for the first frame and motion vectors for all the frames. So the motion vectors, that's something that you transmit anyway in standard video, and the edge map is, it's included in our overhead anyway. Okay. So we have that. So there's a graph. We also assign different weights depending on whether the links are temporal or spatial, with the idea that temporal correlation is high if you identify it, spatial correlation not so high necessarily. So you may not have a very strong edge, but still the spatial correlation is not that high. Yeah. So
there are only two values there?
Yes, in this current implementation, yeah. So we basically have one value for temporal, one value for spatial. Yeah, thanks. Okay, so we apply the lifting transform. Remember, in the lifting transform, we have to do the bipartition, and so there's a bunch of ideas on that. I'll just give you the sort of the high-level idea, which is that if you had a graph where large weights indicate good prediction, high correlation, and low weights indicate poor prediction, clearly you would want to eliminate those links that have the lowest weights, right? So that's reasonable, and so we apply a graph cut algorithm where, as in this example, we would assign these colors. Okay, so these are even, these are odd. And you can see that the links that are eliminated between these two, for example, or these two, are the lowest weight, right? So you would like to eliminate links of low weight. That's we apply that. There's a bunch of other things. This is an ICIP 2011 paper, and this comparison, of course, would not stand the scrutiny of my friends in the MPEG committee. But you know, it's just a very simple baseline comparison where we do a DCT-based encoder and a graph-based encoder. And the reason you see this crossover point is that we're not scaling the amount of overhead to the bit rate. So at very low bit rates, we're sending too much graph information, essentially. Okay. So, but you know, it looks encouraging. It's an interesting direction to pursue, in my opinion. Okay, so this was the first example. The second example, sort of in a similar vein, is EdgeAware image processing, where we go back to standard images. As I said at the very beginning, images can be seen as pixels, vertices that are connected through edges to their neighbors. And you could start with some arbitrary connectivity. You know, the images could be 4 connected, or you could have them 8 connected, as in this case. Or you could go beyond that. Okay. So let's say, for the sake of discussion, let's start by assuming that there are 8 connected images. Remember that we can only do this graph filter bank idea with bipartite subgraphs. Okay? So we start with 8 connections, and then we end up with these 2 subgraphs. Okay? And what you can see is that instead of doing this row-wise, then column-wise filtering, we're going to do filtering in this graph, where each color represents, you know, a color, and then that graph. Okay, so it's a different flavor of the decomposition. On top of it, we can now also apply different weights to the edges. And so, for example, if we have information about the strength of some of these edges in the image, we could choose to disconnect completely some parts of the graph if there's a strong edge. Okay? And the notion of what would be smooth would change. If the more edge information we include, the less information there will be in the graph wavelet transform domain. Okay, so that's the basic principle. This is an example, which of course you cannot really see maybe in the overhead screens. This is the standard Dobeshi's 9.7 filter, and this one would be the graph QMF solution. And you can probably see that it has a little bit less energy. And the reason is that we included some information about the edges. Okay, thank you. And maybe more interesting here, this is a nonlinear approximation representation. So this is the percentage. We include always the low pass, and this is the percentage of high pass coefficients included. And you can see that the PSNR goes up. And I want to point out the difference between these 2 curves, which are the weighted and unweighted graph. Okay, so basically the idea is you can introduce you can capture some of the information in the image by adding weights to the graph, and then that allows you to represent better what's left. Okay, so at some level, if you include weight information into the graph, then what your wavelet coefficients represent a signal with less energy. It's a smoother signal. Okay, and this is something that we're studying. So even for images, I think this has some potential to be used. Okay, the next example is actually something that we started with, which is sensor networks. And the idea there was to do some kind of data gathering. So you have a node, the sink, that is gathering information from all throughout the network. And this could be, let's say, information about temperature. And the idea is that because the information in the network is spatially correlated, one can do better than sending raw data. Okay, so one alternative would be raw data is captured at every node, and then forwarded to the sink. Then the sink has a picture of the overall temperature in the system. The approach that we're proposing is to perform some decorrelation as the data traverses the network. So essentially, as the data flows through the network, we perform a transform and quantization, but it's a distributed transform and quantization. So if you want to look at this as from a graph perspective, I don't have that slide, but you can basically imagine a routing tree And then you say, well, in the routing tree, that constitutes a graph, and we're going to do a transform in the routing tree. How do you do this? Well, if you use lifting, all you need to do is assign even and odd parities to the nodes in the graph. And the very simplest approach to do this is to assign parity as a function of number of hops to the sink, so essentially leveled in the tree. So you could say, okay, this is an odd node, even, odd, even. And you can see that in this case, because it's a tree, you don't lose any connectivity, right? I mean, basically, there's no, the tree is automatically a bipartite graph. Okay? And you can say that even without knowing the distances between the nodes, as long as the topology remains unchanged, you have a way of constructing a transform that is automatically invertible. Okay? And we have done quite a bit of work on this. And just to give you a flavor of what we have, let's say this is the routing tree. These dashed lines correspond to broadcast connections that are not directly in the tree. I'm not going to get into that. But the main thing is that if you consider the quality of the reconstruction versus the energy that is consumed transporting things through the network, you can see that raw data does much worse than any of these two transforms. So doing a transform actually helps. Another interesting thing is that there are two types of transform, one that corresponds to the hard filter in standard signals. This one corresponds to a longer filter in the regular signal. And you can see that the shorter filter does better. And this is because it's in terms of energy consumption. Okay? So implementing a longer filter in a distributed manner means spending more energy transmitting from node to node. So it turns out that you can get more decorrelation, enough decorrelation for the cost with a short hard filter. All right, so that was one more. Okay, so let me end with a couple of applications that are brand new. This one is a paper that is going to be presented in 2 weeks, so it's not published yet. So we're looking at the graph that comes from a Markov decision process. And so imagine a scenario where we have a sequence of states and then a sequence of actions. And we're testing this with network protocols, right? Where maybe your state is a state of a buffer or number of retransmissions in a queue, and then the action might be to transmit or not transmit that particular packet. Okay. And of course, you can see that for every state, in this case, we have T states and two actions. The actions are A0 and A1. You have a potentially complex graph of transitions that says if you're state 2 and you take action 0, you could go to state 3 and action 1, for example, or go to state 3 and action 0. So there's various possibilities. What we're interested in is the graph signal that we're interested in is some notion of a discounted cost for the states. And so that could be basically if you're in a particular state, what is the cost from that point forward of taking one particular action. And what we would like to do is not learn what that value function state is, and also facilitate computation, maybe compression optimization, and so forth. And okay, this goes back to the motivation that I gave at the beginning, that if you have a very complex graph, operating with a smaller graph might be advantageous if you can learn or optimize it faster. Okay, so if this was the original graph that we were working with, it would be nice to operate with a smaller graph, learn or optimize that graph, and then translate the results to this one. Okay, so this is just a very simple example. This is the a planar representation of the state space of this particular graph that we're considering, where we have that these blue areas correspond to no nodes. Actually, this is related to this one. There's a node that connects to all of these, and all of these can be represented in 2D. And I think this one was a retransmission count and buffer side. Okay, so these two things go in integer steps. And after doing the graph QMF transform, you can go from this graph to a low-pass representation, which you can see approximates very much what we have in the value function in the original graph. And then the high pass information, which is, has much less. This is a very smooth value function. Okay, so most of the information is in the low pass. And so essentially what we do here is optimize policy based on the subsample graph versus optimizing policy versus on the general graph. And this is the error between these two. And basically you can show that you can get a pretty reasonable estimate by first operating in a subsample graph and then interpolating back to the original graph. There's some related work that we've done beyond this one that also looks at learning transitions and other information in the graph. And again, if you have a limited number of observations, it's easier to learn transition probabilities, fewer transition probabilities than more, right? So to learn about a smaller graph is easier than to learn about a larger graph. Okay, again, very much work in progress. This is also work in progress, and I'll finish with this one. This is a graph-based prediction for a recommendation system. Okay, so analogous to the Netflix challenge that I'm sure you've heard about. So in a collaborative filtering problem, let's say for movies, we have movie ratings from a number of people, and we would like to identify candidate movies for one particular user. Okay, so there's always going to be a graph. Okay, so the graph in this case is, let's say, movies are the vertices, and the edge weights are the correlation between the evaluations of those movies. Okay, so if you have one romantic comedy and an action movie, it's unlikely that they will get the same ratings from the same person. Okay, so we look at the correlation in ratings that one person gives to both movies, and that gives us a correlation between the movies. So the graph itself is movie to movie, and the weights in the graph correspond to likelihood that or correlation between the evaluations that same users had for those movies. Okay, so now the scenario we have, what we're interested in doing is we're given a movie for which, for a particular user, we don't have rating, but we have a number of movies that are connected to that one for which the user has expressed a rating. Okay, so the graph itself comes from the ratings of many users. Okay, but then we look at one user and we say, this user has rated all these movies. All of them are connected to this one, and the weights come from the evaluation of many people. Okay, so a standard technique for this kind of approach is the k-nearest neighbor approach. So essentially, you look at the graph for which you wish to get a recommendation, for the node for which you wish to get a recommendation. You get k neighbors, and you do an average, a weighted average based on the recommendations for all these other.
So what's the node there? What's the initial node?
This is an unknown movie.
Unknown.
For one particular user. This is the graph that is obtained from the average, and each of these are ratings, known ratings for that user. Okay, so if I watched 10 movies and I rated them on Netflix, then you will have a graph where you have 10 neighbors for any one movie that I want to rate, right? And so,
and it's this user's rating
That's
that
right.
is unknown. We know
That's
the
right.
rating from lots
we
of
know
others.
ratings for many users, yes, but for this user we don't know it. Right? Okay, so k-nearest neighbor is fairly well established technique, and you just do an average, a weighted average, where you take into account the weights of these links. So what we've done is we'll say, well, in addition to these links, other information. You know that this movie and this movie are related by a link, and so we ask the question, well, what can we do by having a more complex or more complete graph? And there are other details that I'm hiding here. But essentially, we pose this problem as an interpolation problem. And we designed the filter for interpolation based on spectral characteristics of this graph. And based on that, we do the filtering. And so it's, you can see it as an extension of the k-nearest neighbor approach. But really, the extension comes in two parts. One is we consider a more complete graph. And two, we design the filter to use for interpolation based on the topology of this graph. Okay. And this gives you an example of how the system does, and it's really systematically better than K-nearest neighbor, the K-nearest neighbor approach.
Is that what's being used now?
This would be a simple approach. There's these non-negative matrix factorization techniques that tend to be more global. There's other methods. I would say K-nearest neighbor is a simple local method. Okay, there's probably not state of the art probably will look at more global information. But in a sense, what we're proposing is a direct extension of K-nearest neighbor that captures connectivity beyond just the unknown movie to neighbor connectivity. And this shows that the number of, basically, the prediction improves as the number of neighbors increases, and this error is computed because we have the actual rating of the movie, right? So the rating is on a scale of 0 to 5. So you can see that you come to within 1 on average, and certainly a lot better than K-nearest neighbor. Okay, a lot of details that are not here. This is hopefully going to be in ICASP submission that we're working on. All right, so let me conclude, amazingly on time. So things that to remember from the talk, we talked about downsampling and upsampling. There's really not very much work that has been done on this topic. Once we understand the downsampling and upsampling, we can look at the critically sampled design. And we talked about a number of applications. And there's really a lot of work in the bipartite decomposition, in the understanding of sampling that is going on, as well on the applications. Okay, so a lot of work going on. I'm very excited about some of the stuff that we're pursuing. And I'll just end with this summary. Again, some theory on a couple of different flavors of design. And I wanted to give you also, the diversity of applications. I think there's really lots of things that you can study if you start taking a graph perspective and thinking of signals as opposed to just thinking about the topology of the graph. And a lot of the work, even in the case of spectral graph theory, used the spectral graph theory, the graph Fourier transform, mostly to understand the topology of the graph. But we think it's useful also in terms of understanding signals that are present in the graph. Okay, so let me stop here and take any other questions you may have. Thank you.
Any questions? No questions? Wow, that was super clear.
Or the other way around, right? It's
Could you speak a little bit more about the variety of approaches to locality? That seems to be one of the interesting angles you're analyzing things from.
In terms of the filtering?
Yeah. Well, it seemed like each of the applications you gave as examples took a different approach to it. So I'm just looking for a contrast in the context of locality.
In terms of the applications?
Yeah.
Well, we're looking at locality in the graph. That's the main thing. And if you look at the existing techniques, the graph Fourier transform, if you have a fully connected graph, each of the eigenvectors is localized in the whole graph, right? So that has no locality. If you look at the spectral-based techniques, diffusion wavelets, the spectral graph wavelets, they also don't have any locality other than indirectly by having a polynomial transform. And I think we're considering locality explicitly. Locality is easy in the case of lifting because you just the design itself is in the vertex domain, so you decide how many hops away you want to be. But those filters don't have a very good interpretation spectrally. So I think we want to have both things. Okay, we want to have a way of defining localized in the sense of being a few hops away transform, but also having transforms that have some meaning in the spectral domain, so that you could potentially answer some of the questions that you would do by analyzing the spectrum of the graph by doing only local processing. That would be one of the goals. I'm not sure if I answered your question.
I think so. I'm seeing that the locality is implied by the structure of the graph. The structure of the graph is implied by what transform you choose. And because of the degree to which locality is so important in your approach, that puts a lot of weight on what transform you choose.
Well, so let me say that the transform you choose really depends on the application. And the graph you choose depends on the application. And then if you want to use the graph filter banks, then you need to do a bipartite approximation. Okay? But you can define the graph essentially depending on the application. Right? And that's sort of what I wanted to do to illustrate with all these examples. That the graphs that we chose there, tend to depend on the application, but they have to make sense on their own. And then we figure out how to do the transform. So the graphs themselves, yes, they're application dependent. And then the approximation, the bipartite approximation, should take into account application specific ideas, right? For example, in the video case, preserving the high weight links, right? But as a first stage, I would say, it's best to think in terms of completely arbitrary graphs that make sense for the application, and decouple that from how the graph is approximated once chosen in order to do the transform.
Jen, do you have a question?
I have a question. Probably I missed something, but I just asked, can you expect the difference between a graph with discrete weight and continuous weight? Because some graph here, the weight is continuous, like between 0 and 1. Some kind of graph we get is just either this edge between two nodes or no. Can you give some intuition about, on this method, what will be the difference between this kind of two graphs?
So yeah, I'm not sure if there will be a difference. In some cases, we have to work with normalized graphs, where you either sum the number of, basically you normalize either by the degree, which is the number of connections, or the sum of the weights of the connections. So I'm not sure how much of a difference it would make. I would say that considering images, one thing that we've observed is that it's generally easier to work with graphs that are fully connected, but have edges that are, some are small weights, some are large weights. That's easier than working with graphs that are sparsely connected, because in some sense, when you talk about these transforms, every time you have a disconnection in the graph, it's almost as if you have a boundary condition for the transforms. And frankly, this is something that we're still trying to understand in detail. The biorthogonal paper that we're submitting provides a discussion of two types of normalization and how they should be used. And there's all kinds of things that are fairly different in graphs. So for example, if you use a normalized graph, the zero frequency signal is actually not a constant. And if you're dealing with images where the zero frequency, a constant image has a meaning, that maybe that's not a good solution, right? So I think we try to exploit the analogy. At the same time, the analogy doesn't always extend that easily, and there's some cases where there's some very specific criteria that depend on the type of signal that you're analyzing that need to be taken into account.
Any other question?
Yeah, one more. On your example with video coding, you're currently using a binary flag on the weight to say whether it's spatial information or temporal information. I'm curious if you've considered preserving some of the information from the edge detection algorithm in the spatial information, and possibly including additional frames and weighting the distance to the future frames.
Right. So in fact, in the current version, we don't explicitly send a graph. What we do is we send motion vectors and then an edge map for the first frame. So that's what we represent. And basically, the decoder recreates the graph because the graph is implied by those two pieces of information. Okay. So the edge for the first frame, the edge map for the first frame is also propagated across time, right, by using the motion vectors, right? So if you have a block that has an edge in it, and then you have a prediction in the next frame that corresponds to that block, then you carry that edge to the next frame. You can, from a transform point of view, the weights could be anything. It just becomes an issue of overhead, right? That if you want many different values for the weights, you have to signal those. One area where we don't have that constraint is actually denoising, and so we're exploring using these kinds of filters for denoising, where you estimate the weights based on the first image, and then apply filtering using those weights, and then you sort of iterate. So that's one area we're pursuing. But for coding, from the transform perspective, yes, you can use different weights, but it has to be worth the overhead, and that's if not, then you cannot gain encoding.
Thanks.
Yeah.
In EdgeAware image processing, you said.
Can you speak up, please?
Yeah. In EdgeAware image processing, you said you sent a edge map in the first frame.
Yeah.
But what if the environment is variable or constantly changing? So you would have to send an edge map after every frame, right?
Well, so in the video coding case, so in the EdgeAware image processing, we haven't really evaluated that for video, right? So it would be one frame, one image, one edge map, okay, and then you figure out what is the right amount of edge information. We've actually been quite successful with using this for coding depth images, because depth images usually have very little texture, so they're just different integer values for the depth. And we've integrated an approach that uses these graph-based transforms with encoding of depth images. And it's block-based, and at every block we decide, is it worth it or not? Okay, we can choose the edge information for each block. Okay, in the video case, okay, so you start with one edge map, and then you carry it over. If there is a block in any frame that is not predicted from blocks in the previous frame, that block doesn't carry any edge information, right? So the temporal prediction tells us if we should carry the edge information or not. Okay, and in a typical video coding case, if there's a complete change of frame, you would have an intra-frame. So our method could also work with that, right? Whenever there's a scene change, you would have an intra-frame, and then you restart the edge information. So that.
Prediction fails, you would send an edge map again.
Yeah, that's really not what we do in the current version. We just send an edge map for the intra-frame, and then we carry it over to the next intra-frame, right? But you could do what you describe as well. Yeah, if there is any block that is coded intra, then you can estimate the edge and send it. And in the case that I presented there, the edge information is fixed and doesn't depend on the rate. But a much better approach would be to block by block decide if it's worth sending the edge information or not. This is what we do for the depth coding case, right? And that's really the approach you would do for any video encoder. You have several possible modes, and you choose the best one.
I have a question. So at the end of the day, basically what you're trying to do is you're trying to do a space scale analysis, and where your space, of course, is defined sort of by this arbitrary structure of your
Right.
graph. But it's not obvious to me, though, that depending on the choice that you're making for your so-called even and odd nodes, that what you'll be getting is necessarily what's underlying the process.
Yeah, it's not a simple problem. And so with the even odd assignment, I mean this is one I described this idea of having a sort of multidimensional approximation, and then we have algorithms to select even and odd nodes in that case. But we're also exploring techniques that are sort of 1D. And so there are some results that talk about which nodes could be eliminated and recovered. I mean, so they can provide some kind of sampling theorems for graphs. But because the graphs are completely regular in topology in general, this could be very different from what you're used to. And so it could say that, for example, if you want to preserve frequencies from 0 to 1, so the middle range, it may say that you can only downsample 10% of the nodes. And
plus the fact that not all edges are created equal, right?
Right.
Depending on how the structure of your graph is
Yeah.
is done. If you have like a large concentration of
Right.
Nodes that are linked,
right.
it means something. If you don't, it means something else.
Yeah.
So it's not very obvious to me at all.
No,
that,
that's why I'm saying there's lots of open questions, which I think is good.
All right, let's thank our speaker again.
Thank you.